Are there any questions? Yeah, I may need to start taking attendance and be bored today. Does someone have a piece of paper that we can pass around for attendance sheet? Without ripping it out of a book or something? You have it? Okay. All right, so let's begin with a little bit of a review. If you remember, what we found, what we argued in the last class, was that even though control is a difficult problem, it's possible to do control. Control is possible, but it involves coming in at the best way is it involves coming in at the design stage of the plant. If you come in at the design stage, then you can make sure you can identify all the variables that need controls, and for each of those variables, you can make sure that there's a manipulated variable that will affect it. So you make sure that there are enough valves, heat exchangers, etc., in order to control all of the control variables that are needed. And you also make sure that the range of flows available for those valves are large enough that they actually have a significant impact on the control variables. Now, of course, old plants that are 50 years old or older, before people started worrying about greenhouse gases, before people started worrying about energy costs, when energy was cheap, they have lots of buffers. Generally, those plants are not strongly integrated. So if there's a hot stream and a cold stream on different ends of the plant, and the cold stream needs to be heated, they would just use energy to heat the cold stream instead of contacting the hot stream with the cold stream. You have it's a lot easier to control things there because you can just add stuff. If you need another heat exchanger, you just turn, if you just need to heat something up, you just turn a boiler on. More recent plants, particularly much more recent plants, try not to waste any energy. So what they do is they integrate the plant completely, or as much as possible, so that if I have a hot stream here that needs to be cooled and a cold stream there that needs to be warmed, we contact them with each other in a heat exchanger. And that way we save energy instead of sending the hot stream out to the environment and using a boiler to heat the cold stream. The negative side, that's of course a wonderful thing. The negative side of that is that if there's a disturbance in the plant on the hot side, it will then affect the cold side. So disturbances will propagate through the plant more, so control is much more essential. And that's one good reason why we have this class, so that you have a sense of how to do that control. Part of the control, in addition to designing the plant so that it has the right number of manipulated variables that can influence all the control variables within the right range, is also having a proper model of how to adjust the manipulated variables to the control variables. And that requires some understanding of how the plant works, and we will get to that. We'll start getting to that later today. The one thing to be careful of is control equipment is not cheap. So we have to do a careful design because you want to make sure that when you spend money on control equipment, that it actually works. So let's just talk a little bit about control strategies. Let's say I have some sort of chemical reaction going on in a CSTR, and I have the feed coming in, and I have to heat up the feed for it to actually react in the CSTR. So so I might have some sort of catalyst in the CSTR. When it comes out of the CSTR, I put it through some sort of separation device, and then the bottoms go through another separation device, and the desired product is all the way here on the bottom. So you can think of these as two distillation columns, if you want, operating at different temperatures. And let's say I'm interested in the product here. And so one thing I can do is if the product is not what I want, then possibly the reaction didn't react far enough. So maybe the feed was too cold. If the feed was too cold, I didn't get enough reaction, so I didn't get enough product. So what I might do is I may have some control that adjusts the flow rate of the heating fluid to heat up the feed based on what happens on the outside, based on what happens at the in the product. Well, what can happen there is there's a lot of events that go on between the heating and the actual output over here that I'm measuring. So, of course, I have the reactor, and I have the first separator, and I have the second separator. So, what I could find is that the concentration I'm measuring versus time could actually oscillate quite a bit because there's a lot going on between here and here. Yeah?
I'm sorry. What is the same circle?
The circle AC1, A is analysis, C is the concentration, and this is the first concentration analysis. There's only one here so far. So that's one situation. Now, if I don't like all those oscillations that can be happening, or a large range of what's going on, because I don't particularly like, this could be the product quality. I don't want it flipping all over the place. What I might do is I might add some other type. I may take some other control, and so what I might do is I might control from here. I might put an AC2 here. And instead, I might look if there was something going on in the temperature of the feed, then it would already show up at the exit from the CSDR before I get to the separators. So what I might do is I may have much more immediate control of the temperature. And I may or may not leave this as well. And chances are, if I start doing this control earlier, then my concentration at the output should have much smaller variations. So this is sort of a strategy of control that I might want to do the control early rather than late, or maybe both, to try to minimize these variations. So that's one situation that could be interesting. Another situation is if I have a very exothermic reaction. In a CSDR. So it's very exothermal, maybe I should say exothermal. So a very exothermal reaction and in a CSDR. And what I want to do is I want to make sure this thing doesn't blow up. So so one thing I might do is I could have some sort of cooling here. And what I could do is I could measure the temperature here. And if the temperature is too hot or too cold, I can influence it by altering the flow rate of the cooling fluid. Another thing I can do is if I have, for example, if I'm also controlling the level, so I don't want it to overflow, then I could also measure the level. And for the level controller, I can control the flow rate. So if I have a very exothermic reaction, it's very important to control the temperature. So let me control it directly by measuring the temperature and then adjusting the flow rate of the cooler. So these things are basically common sense so far, but they're something that's important to do. Another situation. Yeah. Could you speak louder so I can hear you?
So the public for AP's analysis, I'm sure the other was not being analyzed.
You can put the A in if you like. Yeah.
Previous example, you have two control systems. You have like 2,000 series or
No, here, no, see, see what would happen here is this would go into a calculator. The dashed line, which we haven't detailed yet, we're going to get to that. There's going to be a controller here that does a calculation based on this value and this value, and then controls just the valve. What you don't want is two separate controls working separately, fighting against each other, which I think is what you're getting to, which is a good question. So what would happen here, and we'll get to it later, is it's not that these would be controlling it separately, is that the output of AC2 and AC1 would go into a controller that has a model of the system, and then it would decide on a single output of what's going on.
Can we replace the valve after the pump to control the level of inside?
I'm sorry, yeah, typically we would put the valve after the pump.
So what would be the is it the same or?
Well, the main difference, the reason why you put it after the pump, and it was my mistake for putting it before the pump, is if you ever want to shut it down, you don't want the pump to go dry. So if you put it before the pump, and you stop having fluid going into the pump, then the pump can break. So, and you're right for pointing it out, when you put it afterwards, if I shut this, the pump still remains wet and full of liquid. Thank you for pointing that out. That was my mistake. Question?
In the first diagram, the second oval, do you have a line pointing down?
This is going in the middle.
No, for the other lines, the right side, left.
Yes, yeah.
Is that pointing down directly, or I can't really see that? Okay, got it.
Other questions? Okay, so let's look at another situation where I have two streams that I'm mixing. And I'm doing sort of a simple mixing. I'm mixing it in one CSTR and then going into the next CSTR and then mixing again in another CSTR. And I'm looking at what comes out. So the idea is I have two streams, 1 and 2, and I want to make sure that they're really well mixed. So I mix them in 3 separate CSTRs. And I measure the concentration. Now, the simplest control system is if I'm not getting the right, let's say this is A and this is B. If I'm not getting the right amount of B in there, so then I might measure the amount of B I have here, and then adjust this valve. If I'm getting too little, then I might want to open the valve. If I'm getting too much, I might want to close the valve. So if I'm looking at my output, what would the output look like? So let's look at the output. If I have simple feedback control, so let's say this is my desired valve. And let's say there was some sort of fluctuation A. So let's look at the input, A. So A was going along nicely, and then it went up, and then eventually went down. That was the input of A. And I would like to look at the output of B in the product. Now, and actually, let's just take something even simpler, just a step change. A went up. So what happens if I have simple feedback, as we'll see, we'll do some analysis. So again, let's notice this is the input A as a function of time. It was at a certain value, and then there was a fluctuation, and it went up to another value and stayed there. And I'm looking at the output, sorry about it. And let's say I started out doing okay. Now, if I have too simple a feedback control, and we'll see this a little bit later, then the output could look something like this. That is, the output could adjust, but it may never go back to the desired value if this is for too simple feedback. and it gives me what we call an offset. On the other hand, if I have a little bit more sophisticated feedback, and this is stuff that we will go through later in the semester, I might have something that looks like this, and then eventually it does go back. Better feedback. But what you can see here is that in order for the feedback to actually kick in, to really work, it has to wait a while until the error builds up. So when the output is only a little bit off, when I'm only here at the output, feedback isn't doing much because there isn't much of a difference between the instantaneous value and the desired value. We don't really get much of an effect of the feedback until there's a big difference between the desired value, the actual value, and the desired value. So even with better feedback, we can get big excursions. This is an excursion. We have to go pretty far away from where we want to be before the feedback really kicks in. So one way of trying to remedy that, again, this is control strategy, might be to add some what's called feed forward. So for example, we said that there could be a problem in the input. So if I measure AC2 here, if I measure A in the input, then I will immediately notice that there was a problem in A before I get to the output. So if I do this, then I can also have, and this part is feed forward. This is feedback. And again, we don't have the two controls fighting against each other. What I mean by this is the two of them, the two signals get fed into a single controller that gives a single command to the valve, just the way I drew it. And if I do that, then chances are I might never get too far. Because as soon as I get a little, as this happens, I'm going to start to react. So this one is feedback plus feed forward. So you can see that there are different strategies to control, and we need to know which one to choose and how to do it well. Again, this is all qualitative. We're going to get quantitative. Don't worry. There won't. One complaint I will not hear in this class is there wasn't enough math. That's not good. There may be other things you don't like, but you won't say there isn't enough math. Okay, so what are our goals here? Our goal in control is minimum variation. We don't want these long, big excursions if we can't have them. We also don't want offset. And we also don't want it to take forever to get back to the desired value. However, if we overreact, we could get oscillations, and we definitely don't want oscillations. So there are lots of things that we don't want. What we do want is a steady state at the desired value. In order to do that, we have to understand the process, and of course, whatever control we do has to always be within the full safety guidelines. Okay, so we need some questions for models. So we've spoken about equipment, that there's certain equipment, what we like to do, feedback, sometimes maybe mix that with feed forward. But what are the questions that we would, but in order to actually know what these dashed lines are doing, I just drew them as dashed lines here, but to know what they're actually doing, we need a model of the system. And so we need to start thinking about how you put together models. So in order to figure that out, there are a number of questions we ask. Which variables can we influence? Now that goes into the design of the plant. You want to look at all the controlled variables and make sure that all the important variables can be controlled and that you have manipulated variables for each. I know I've said that before. And you want to make sure that the range makes sense, that you can control those variables over a proper range that's within the operating window. So that you could, it's pretty useless to have a control variable that can only change the manipulated variable that can only change the control variable by a tiny amount. You want to be able to change the control variable by an amount that's adequate to keep it within the control variable, within the control in the operating window. Now, of course, once we start doing control, we're going to focus mainly on feedback control. But one obvious question is, with feedback control, how good is feedback control at keeping us within the operating window and achieving the goals? Sometimes it may, as you see in this particular case, it may not be good enough. We may need to enhance it with feed-forward control, where that might be advantageous. We would like to know we would like to be able to, from our model, relate how much I change the manipulated variable to its effect on the control variable. And that's very important. That's really where the model comes in. If I need to effect a 10% change in the control variable, how much do I change the manipulated variable, and in which direction do I change it? And that requires some understanding of the system, which we're going to be doing when it comes to modeling. We'd also like to understand the speed of the response. When I change the manipulated variable, how quickly does the control variable change? If it changes too slowly, well then I could get very large excursions because I changed the manipulated variable and it takes forever to have an effect. So for example, over here, if I change this manipulated variable, it's going to take a while to affect this because this is far downstream. On the other hand, so if it's too slow, I can get large excursions. If it's too fast, I can over-control and I can get oscillations. And the example I gave in the first class, when you're in the shower in the morning, and if there's if you over-control, well, what happens? The water's too hot. So what I do is I turn the hot water down a lot to cool it down. Well, if I overdo it, then all of a sudden the water's going to be too cold. If it's too cold and I'm still over-controlling, then I'm going to turn the hot all the way on, then it's going to be too hot, and it's going to oscillate up and down. That's obviously undesirable. So you don't want to over-control for the response to be too strong, and you don't want it to be too weak. Again, we'll be getting to these things. We also don't want too much of if it's too slow, again, there's also a big lag time between when this goes up and when you start seeing the response of the controller. We'll, again, talk about all those quantities in detail as the semester goes on. And of course, why are these excursions, why are the large excursions important? Sometimes, let's say we're talking about a temperature excursion in a reactor. If the reactor is a catalytic reactor and the temperature goes up too much, even if it only goes up for a minute or two, it could deactivate the catalyst. So even though eventually you go back down to the desired temperature, if you go up too much for a couple of minutes, you can ruin things in the reaction. So sometimes these excursions are very, very undesirable. Sometimes you don't mind, but sometimes they're awful. So in order to actually understand these things, to know what to understand how to take the output of the measurement and turn it into and control the manipulated variable, you need a model. And there are various types of models. So, for example, there are theoretical models and experimental models. Sometimes the system is so complicated that you may want an experimental model. And I believe you would have spoken about this in your 341 in fluid mechanics class. So, for example, there's this race of yachts called the America's Cup. It's a very famous race. And so you have different teams racing on the ocean with their boats to try to get someplace. And I don't believe it's with a motor. I think it's with the wind. But they're all exposed to the same wind. The bottom, the shape of the hull is very important for how much resistance they're going to have in the water. And this is generally a very tightly kept secret, how they actually make the shapes of the hulls. So, and the fluid mechanics of that is quite complicated. You can try to simulate it, but at the end of the day, what they actually do is they would like to have a physical model much smaller than the actual ship and actually measure the resistance in the water. And in order to do that, to have an experimental model, you have to make sure that you have dynamic similarity. Dynamic similarity means you write down the overall governing equations, even if you can't solve them. You non-dimensionalize them, and you make sure that the non-dimensional groups, like the Reynolds number, the Froude number, etc., the physical ratios, are the same in the model system as they are in the big system. Because if there's dynamic similarity, then even if you can't solve the equations exactly, you know that both the small system and the large system, when they're non-dimensionalized, will satisfy the same equations. So that's an example of an experimental model where if you guarantee dynamic similarity, then you can get useful information out of that without solving a lot of equations. Or sometimes it's so complicated that you don't believe you've included everything in the mathematical model, so you still want to do the physical experiment. So the first dichotomy is theory versus experimental model. The second one is if you decided on theory, then the question is, do you use a fundamental model or an empirical model? That is, a fundamental model is one that's based on first principles, on physics, on chemistry. An empirical model is what everyone's using today, AI, artificial intelligence. You basically just do a correlation of a whole bunch of measurements. That's what artificial intelligence is. It is a fancy correlation that takes measurements that have been made until now and tries to correlate them and then make predictions. Those kinds of correlations are great, are often very, very good and fast if the new system that you're trying to predict is somewhat similar or between the systems that you've already used to train your model or to train your correlation. If your new system is very different from any of the systems that you've used to train your model or your correlation, then all bets are off. And then you're much better off with a fundamental model. Okay, so theoretical, experimental. Under theoretical, you've got fundamental or empirical. Under fundamental, so maybe I can even write this, so models. So you've got, as we said, you've got theoretical or experimental. Under theoretical, you've got fundamental or empirical. Under fundamental, you've got either steady state or dynamic. Steady state are all your courses until now. So that's steady state land, that's fantasy land. In this class, the models are dynamic because they allow things to change in time. That's actually why we need to control. Now, another way of breaking up fundamental we could break up fundamental as a lump parameter or distributed parameter. So for example, lumped distributed might be, if you're doing fluid mechanics, you're looking at the velocity as a function of position and time. In lump parameter, you just assume that, don't worry about how the velocity changes with position, you just take an average velocity and look at only how it varies with time. Typically in lump parameter systems, if they're steady state, they're just algebraic equations, whereas distributed parameter are differential equations. You can think of the difference as lump is unit operations and distributed is transport phenomena. And of course, once I have a model and I've decided which one to do, I need to know how to solve it. So the solutions, I can either look at analytic solutions or numerical. Now, of course, an analytic solution, when it's possible, it's not always possible. The nice thing about an analytic solution is from an analytic solution, you can see immediately how the different inputs affect the output. If I have a formula, again, you don't have to worry about writing everything down because I'm going to take pictures of the blackboard and post them, and we have a video of the class. So you can write whatever you want to write, but don't stop listening because you're writing. If it's a choice between listening and writing, listen. If you do them both, great. But the idea is if there's something you don't understand, to be able to ask right away and not 2 weeks later when you realize you don't understand. Okay, so in an analytic solution, if it's possible, then you come up with a formula and you can see how the change of any of the inputs affects the output because you have a formula that gives you the output as a function of the inputs. If it's in the denominator, then you know as the input goes up, the output goes down, etc. In a numerical solution, you don't have that unless you've done a million simulations. So when it's possible, it's nice to have analytic, but if not, then you use numerical. And today, the numerical procedures are quite good. In the old days, meaning 50 years ago, there was a third way, which was to use what's called an analog computer. Now, what's an analog computer? Later on in the semester, we're going to use a program called Simulink. Simulink is made by the same company as MATLAB. In fact, they even advertise on the radio, which I always find is funny. Like, who besides chemical engineers is going to appreciate that when they advertise on the radio saying, we make Simulink and we make MATLAB? Great. I'm sure that advertisement is going to bring you one more customer. In any case, what Simulink does is it has these little boxes that you put on the screen. They used to physically have boxes. So if you wanted to do an integration, so what they did is the variable would be a voltage. And what they would do is they would actually have a box that was an integrator. So you would take a wire from the output of the voltage and stick it into the box that was an integrator. And what came out, it would actually integrate the voltage over time. And if you wanted a derivative, there was another box that did the analog of a derivative for the voltage. As well as addition, there were little boxes that did addition, that did subtraction, that did integration, that did differentiation. So what people used to do in the 1950s and the 1960s is what they would do is if they had a complicated plant, at the time the digital computers weren't as capable as they are now, they were much slower. What they would do is they would simulate the equation with actual physical boxes that did integration, differentiation, addition, subtraction, etc. And then what they would do is they would perturb the voltage at the input and look at what happened to the voltage in real time at the output. And those computers apparently worked quite well. They weren't as exact as numerical computers, but often you don't need exact to 10 significant figures. You just need to know, is my system going to blow up or not? Today, you don't use boxes, you use Simulink. As we see on Simulink, we'll have these boxes on the screen and we'll put them together and make simulations of our plant, of our control system, etc. But Simulink is basically taking the idea of an analog computer and making it digital, putting it on the screen. Sometimes, you go in, if you look in the back room of chemical engineering departments that have been around for a long time, in the storage room, you'll find some of these boxes. You may not know what they are, but you may find them. Any questions so far? Lump parameters, if they're steady state, if the model is steady state, they tend to give you algebraic equations. If the model is dynamic, then they tend to have a DDT, but no derivatives in space. So it's an ordinary differential equation. The distributed parameter, if they're steady state, they tend to give you derivatives in space but not in time. So whereas if it's distributed, if it's dynamic model, then there are derivatives in space and time. So you can think of Navier-Stokes if you're doing a fluid mechanics problem. If it's dynamic, you're keeping the ddt, and you still have the del squared u. If it's steady state, you don't have the ddt, but you still have the del squared u and the del p. Other questions? Okay, so let's say I'm going to do fundamental models. At some point, I will write equations, believe me. But let's say we're doing fundamental equations, fundamental models. There are three types of equations that go into fundamental models. There are laws of physics. There are conservation equations. And then there are constitutive equations. Who did you have for transport one? Did you have Mazzarella? Two. Okay, I don't know what 2,000 equations, but I'm sure Mazzarella makes this distinction. Did two make this distinction? It's a yes or no answer. No, okay. So what's the difference? There are three types of equations that we work with. Laws of physics are things that always hold. So they always hold, or we believe they always hold. And they have no parameters. Can someone give me an example of a law of physics? Don't worry, you don't have to be right. Yes, that's Newton's third law. An object in motion, not on the influence of any external forces, stays in motion. What another law of physics? Don't be afraid, it's okay to get things wrong. F is equal to dp dt. If the mass changes, you want to write it. The force is the time rate of change of the momentum. So an example is the force is dp dt, which is the momentum. That has no parameters, and until the end of the 19th century, it was believed that that always held. Obviously, when you go to very atomic sizes, then quantum mechanics takes over, and when you go to speeds near the speed of light, then things also change. But up until that, we believe, certainly neither one of those is typically dominant in chemical engineering processes. So here you see a law of physics. It always holds. It has no parameters. There are no material parameters. A conservation equation is something that says something's conserved. What do we usually assume is conserved? Mass. Anything else? Mass and energy. So there we might have the mass, dt 0, and we also have an energy equation. Finally, notice there are no parameters here. However, if I want to use, and by the way, F is equal to dp dt is also the Navier-Stokes equation. The left side of the Navier-Stokes equation is the time rate of change of the momentum. Rho du dt plus u dot del u. That is the time rate of change of the momentum of a particle of fluid that's moving. Maybe I can just a little aside here. This left-hand side, this is the mass per unit volume times the acceleration, the time rate of change of the velocity. This is the time rate of change of the velocity locally. But if I have a fluid element, it's moving. The partial derivative is how it's changing here. But that fluid element moved over here. when I go into a moving frame, then this corrects for the motion of the fluid element. So this is the mass, this is the time rate of change of the momentum per unit volume of, if you like, red particles. So you can imagine fluid moving, it's clear fluid, and I paint some fluid particles red, and otherwise don't change their properties. So if I want to calculate the time rate, apply Newton's second law to it, then Newton's second law on the red particles, I have to follow the red particles. So that's exactly what's going on here. The time rate of change of the momentum of the red particles. And this is the sum of the forces. Now the forces, there's a pressure force, there's a viscous force, and there's a gravitational force. But this is exactly Newton's second law for moving particles, for a continuum of moving particles. As an example. But notice that Newton's second law doesn't tell me what the forces are. It says whatever the forces are, you figure them out. So to figure out what the forces are, these are the constitutive equations. So the constitutive equations, this is a constitutive equation for the pressure force. This is for the body force. This is for the viscous forces. So constitutive equations may be Newton's law of viscosity. U tau is I don't want to 1 second too fast. Tau yx is mu du dy. Yeah. So this might be an example of Newton's second law. Another one might be the heat flux is minus K del T. So what you can see here is these are, or another one might be an equation of state. EV is N on T. So these are all constitutive equations. And notice they have parameters. There's a parameter often in a constitutive equation that are material dependent. Another one might be the spring force is minus K delta X. So I have a spring constant. I have viscosity. I have a thermal conductivity. All of these quantities are material properties. So whenever you see something that has material properties in parameters, that's a constitutive equation. And unlike laws of physics, constitutive equations don't have to always hold. They hold for this material, but not for that material. Different fluids have different viscosities. Sometimes I have non-Newtonian fluids that don't satisfy this equation at all. Sometimes I have ideal gases, other times I don't. I have a different constitutive equation. I may have spring, this is a linear spring. So I may have springs that are not linear. If you ever look at springs that instead of looking like this, look like this, where the diameter changes, these are nonlinear springs. They don't satisfy this equation. So constitutive equations, sometimes they hold, sometimes they don't. Laws of physics always hold. So that's an important distinction when you're making models. And when you put together a model, you generally use all of these. If I'm doing a chemical reactor problem, then I have in a chemical reactor problem, I typically have the reactor equation. Now, this semester you're also taking chemical reaction engineering, is that correct? So you probably haven't gotten to them yet. But we have the types of reactors that you generally deal with are the batch reactor, the plug flow reactor, and the CSTR, continuously stirred tank reactor. I imagine you've heard these terms in 228. And you may have actually even come up with the general steady-state equations. So the reactor equations, so for example, the you could have the steady state equation, you can have, well, the steady state thermodynamic equation for these reactors. I'm not going to write them down right now. I'll write them down as we need them. But these reactor equations function like a law of physics. In other words, they're not really laws of physics, they're conservation equations, but the assumption is they always hold. If I have a CSTR, I assume the CSTR equation always holds. And if you notice, in these equations, there's going to be something called the reaction rate. So typically, RA might be the rate of production of species A. Now, in order to specify that, I need to specify that in a constitutive equation. So a constitutive equation for that might be A times the product of the concentrations to some powers. So this might be in order to get the rate of production of A, I may have a certain rate of reaction that if I assume it's a standard rate of reaction, a mass action rate of reaction, then I've got a rate constant times the product of concentrations to powers, where the powers are often, if I have elementary reactions, the powers are the stoichiometric coefficients on the tail side of the arrow. And in fact, I may have a bunch of such reactions that either produce or destroy A. So these are constitutive equations, and the reactor equations we're going to treat them as if they were laws. Are there any questions on that? Okay, so let's see where we are. Okay, so why do we use, so why do we use fundamental models? We use fundamental models, again, because a small number of principles can explain a lot of what's going on. They allow extrapolation, unlike empirical models, and they relate system features, they relate inputs to outputs, and they are very helpful in design. So what's the basic idea when you do modeling? So when you do modeling, you have a certain goal. What you do then is you formulate a model. Let's just make sure I'm not leaving out any steps here. Yeah. You formulate the model. When you formulate the model, then you try to solve the model. And then you analyze the solution. That is, you try to calculate the things you need to calculate, and then you validate. You validate the model by comparing it with experiment. If the model and the experiment agree, great. If not, then you go back and you reformulate the model. And eventually, if everything works, so if they don't agree, you have to go back. If they do agree, you're finished. Yep.
Can you tell what to say after the solution?
I couldn't hear you.
After the formulation.
Okay, goal. Formulate model, solve model, analyze solution, validate. If the validation, that is compare with experiment, doesn't work, you have to go back and change the formulation. If it does work, then you have a model that you're happy with. Was that the whole question, just for me to read it? Oh, okay. I was hoping something a little harder. Okay. Sometimes we have quantitative questions we want to answer. For example, if I have a tank, when will the tank overflow? So that's quantitative. I want to know when that's going to happen. Sometimes I just have qualitative questions. Will the height of the tank oscillate, or will it reach steady state? So sometimes I want to answer qualitative questions, sometimes I want to answer quantitative questions. The model can generally do both. So so let's look at an example problem, a simple problem, and let's go through the steps of basically how to deal with it. So, problem. C in. Of course, I got a font V in, V out. To be consistent with your fluids class, I'm going to use a little v for volumetric flow rate. Sometimes people use capital F. Sometimes people use capital Q. I'm going to stick with the in control, a lot of times they use capital F. I don't understand why they have to use different notation in one class from another class. So I'm going to try to stick to the fluids notation, to the reactor notation, where a little v is the volumetric flow rate. And so I have a situation here, and we're given, so this is C in versus time. And C in versus time goes through a step change. And this is going to be really simple in that we're given, for t less than 0, the system is at steady state. And in addition, there's no reaction. So basically, if the system's at steady state, then for t less than 0, there's 0. What goes out, what comes out is the same as what comes in, because it's been moving here through here until it reaches steady state, because there's no reaction. And the question is, and we're also given the volume of the reactor, V is known. And the question is, how long does it take for C out minus C out at T is equal minus C in? Let's see. Let me get the question right. Oh, it's species A. And let me just get it completely right. Copy the question correctly. Okay. Yeah. Okay. So, how long before the output A, the amount in the output minus the amount I started out with? So, this was the value, the initial value. And so the initial value, remember, was for t less than 0. The system is in steady state, and I'm at CA is 0. So CA in. And since I was initially at steady state, CA out was equal to CA in for t less than 0. So let's recall this is CA in, CA out, which is 3. Here's 0. And what happened was CA in and CA out, these numbers are the same. This is a steady state. But now once I have a step change here, something's going to happen here. And eventually it's going to get to the new CA out. So eventually this value and this value should also be the same. But this could take a long time until they're the same. And here I have a region where they're different. And the question is, how long before this reaches 90, how long before this curve reaches 90% of the final value? The example here might be 0.9 times the final value. So I want to find this particular. Is it clear what the question is? So there's no reaction going on. I have a step change in the input. Before the step change in input, the input and the output were the same. There's a step change in the input. Now it's going to take a while for the output to get to the same value as the new input. How long does it take for it to get 90% there? Oh, okay, good. So I read your mind? You didn't know I could do that. Okay, so, yeah. So the first thing to do is to sketch the system, which we've just done, and we've identified the parameter. We've identified the inputs, and we've identified the outputs. We've identified both of those. Now, yeah. So now I need some, the data. Input data. Well, I have all sorts of physical properties. I may need to know densities. If I were interested in temperature, I would have the CPs and the CVs, which I'm not interested here. If I had a reaction, I would be, so I don't need them here. Other input might be CP, CV, the phase diagram, reaction rates, rate functions, etc. But the things in the brackets I don't need for this problem, for this question. But these are types of input data that I would have. I also need to know the volumetric flow rate. So those are all things that I have input data. Now, typically, what are the things I can control here? What are the things that I have control over and the things I don't have control over? So one thing I have control over is I have control over the volumetric flow rate coming in. Something I don't have control over might be fouling. So as time goes on, the pipes might foul, and there might be and for example, the effective volume of the reactor may be affected by the amount of fouling. I have control over the pump that's pumping the fluid in. If I have fouling, the same pressure in the pump might lead to a lower flow rate. So there are things I can't control. Now, typically, I might, after I do input data, I may have some assumptions. So one assumption I might make is that rho doesn't change with constant duration. So a CA, that's an assumption. It doesn't always have to be true. But that's one type of, I need to make an assumption like that in order to actually handle this problem, or some sort of assumption. Okay, so now what I would do is I would try to formulate the problem. Let's see if there's anything else I need to do before I do that. Okay, so in general, when I formulate the problem, I look at the laws of physics, the conservation equations, the constituent equations. So, for example, in this particular problem, it's pretty easy. What I need is the reactor equation. So in this case, I have a reactor equation that I'm going to write down in a second. Before I get to it, I want to mention, what are the conservation equations? Well, in conservation equations, generally, in temperature, we have a mass conservation and we have an energy conservation. When we look at the conservation of energy, what we typically have when we write out the conservation of energy is we have the time rate of change of the total energy, which is the total energy is the internal energy plus the potential energy plus the kinetic energy. The total there is equal to the flow part, the energy that's going in and going out, plus Q minus W, plus the heat being supplied, minus, depending on what thermo you use, either minus the work done by the system or plus the work done on the system, whichever way you prefer defining W. And of course, if I have a constant volume system, then typically, instead of using U for the internal energy, I would use the enthalpy H, and as a result, the work would just be the shaft work. So that's all thermodynamics, which we don't need for this particular problem, but that's something that we do in general. And let's now look at which equations we need. Okay, so how do I know what equations to use? If I am, so here I'm speaking more generally rather than for this particular problem. If I'm trying to calculate a total amount of mass or a pressure, then what I would use is the conservation of mass. So if I use the conservation of mass, is a method for me figuring out the total mass, how that changes, if that changes, by stuff entering and leaving. On the other hand, if I'm interested in the concentration, how species A changes, then I need to do a species balance. I need to do a balance on species A, for example, if I'm interested in how A changes with time. And that can involve in and out as well as production and destruction. Whereas mass is neither produced nor destroyed. If I do conservation of mass, I'm just looking at the in and out. If I'm looking at a species balance, I look at in, out, and also production or destruction. If I'm interested in temperature, how temperature changes, then I need to do an energy balance. So those are the various balances that I could use. And of course, I need various constituent equations. Depending if I'm doing an energy equation, I need to know this constituent equation. If I have reactions, I need these constituent equations. If I have flow, I need these constituent equations. For example, if I'm doing mass transfer, then I also need Fick's law. Now the question is, how many equations do I need? How many equations do I need? Well, we define something called the degrees of freedom. Which we often write as degree F, degrees of freedom. And that's defined as the number of variables minus the number of equations. Now typically, if the number of equations equals the number of variables, then our system is well posed. On the other hand, if there are more variables than equations, then I have degrees of freedom. Then the problem is underdetermined. That is, lots of things can change because I haven't determined everything. On the other hand, sometimes I have more equations than variables. And then the system is overdetermined and something's wrong. So I can, if the degrees of freedom are zero, that is, the number of equations equal the number of variables, then the system is well posed. It could be overdetermined or underdetermined. Underdetermined means I need more equations, so maybe more constraints. Overdetermined means I have a problem. It means I generally can't solve it if it's overdetermined. Okay, so now we need to do determine the variables here. If I have a system, if the volume is fixed, so what are the variables here? Let's look at this particular problem. What are the degrees of freedom? The variables are concentration of A and possibly the volume of the reactor. So, who said that the reactor is full? Maybe the reactor is not full and stuff comes out. So, if I have two variables, then the equations I would need is the reactor equation, well, the species balance on A, on species A. And I would need to know, for the volume, I would need to know some equation that tells me V out is equal to what? So I need to know what the out is. Now, there are many possibilities. So in this case, if I have two variables and two equations, I have my degrees of freedom is 0. Now let me give you some examples of this, some examples. Either V out is equal to V in, which case the volume of the fluid in the reactor is fixed, and then I've taken care of that variable. Or another possibility is V out is equal to some constant K times the height of the reactor minus some initial value, L minus L0 square root. Now where does that come from? That comes from Bernoulli's equation. So let's say I have a tank and I have an L. And this is, say, L0, and this is L. And I want to know how much fluid is flowing out through here. So from Bernoulli, I know that P0 plus rho G L plus 1/2 rho E squared, say at 0.1, and this is 0.2, V1 squared, L1, wholly 0, is equal to P0 plus rho G L0 plus 1/2 rho V0 squared. So I'm comparing this point and this point, just like you do in unit ops. Now, since both are exposed to the atmosphere, P0 is the same. And if the cross-sectional area here is much, much bigger than the cross-sectional area of the pipe here, I can ignore this, because V1 is very small. Now, so what does that tell me? I can count some of the rows, and that tells me that V0 squared is equal to 2GL1 minus L0. Or V0 is the square root of 2GL1 minus L0. So from Bernoulli's equation, we have that the velocity, and here I should use U. This is U. Because I'm stating V for the volumetric flow rate. That's U. And of course, V0 would be U0 times the cross-sectional area of the pipe. So here you can see that K would be equal to A0 times root 2G. So this is an example of if I have a tank and I have a little pipe here with the fluid coming out, and I want to estimate the flow rate through the gravity, I would just estimate the out volumetric flow rate is proportional to the square root of L1 minus L1. So those are possibilities. Are there any questions on that? A lot of times your book just gives you an equation like this without telling you where it comes from. It's easy enough to tell you where it comes from. Okay, so, well, that's an example of a Stitcher equation for V out. How about the species balance on A? So let's do the species balance on the CSTR. Balance on the CSTR. the general equation of chemical engineering? How do you sum up chemical engineering in one equation? Come on, yes? Accumulation is, yes. So the rate of accumulation equals the rate in minus the rate out plus the net generation. In this case, by reaction. There's no reaction here, so I have the rate of accumulation, ChE dt. And I need assumptions. I've assumed that rho doesn't change. So is equal to the in, that's V in CA in, minus V out CA. Now in a CSTR, the assumption is that this regime is perfectly made. So the concentration everywhere in the reactor is the same. And since C out comes from the reactor, you assume that C out is the same as the concentration in the reactor. And if I have net generation, I have reaction. But here I assume there's no reaction because I'm given that there's no reaction. So I have a simple equation, dCA dt, and I need the volume here. The volume times, so CA is moles per unit volume, times volume is moles per unit time. This is moles per unit volume, volume per unit time. So this is moles per unit time. And every term here is moles per unit time. If I divide through by V, then, and I let tau equal to big V over little v. And if I assume V out is V in, then I can rewrite this equation as dCA dt is equal to is equal to CA in minus CA over tau. Have you seen tau before in your reaction engineering class yet? Okay. So tau, first let's just look at the units. V is a volume, little v is the volume per unit time. You don't need to write that much here, you need to listen. This is a concept. V is the volume, little v is the volumetric flow rate. Volume over volume per unit time is units of time. That's time units. So tau is units of time. Tau is often called, it's an unfortunate name, but it's called space-time. It has nothing to do with relativity. What the tau is the amount of time it takes to replace one fluid volume in the reactor. So one reactor volume is worth of fluid. This has become actually quite important in COVID days. What COVID people talk about is how many air exchanges there are per hour in a room. The inverse of that is how long does it take to change all the air in the room. So how long does it take to change from the ventilation system? How long does it take to change all the air? Tau. So the COVID people don't call it space-time, they just discovered it now. We've known about it for 100 years. We call it space-time. Tau. And here is the equation that we have in the reactor. With the noise outside, we can speak up. No, well, that's a more complicated question. Sometimes it agrees with residence time, sometimes it doesn't. If you have a constant density system, it agrees with residence time. If you have a non-constant density system, it does not agree with residence time. So rather than think of residence time, think of its space-time. It's the amount of time it takes to replace one reactor volume with fluid by flow. Again, that coincides with residence time in special cases, but if I have a non-constant density system, it does not coincide. And it's a much more, it turns out this is the important concept, not resonance. This is the appropriate concept, not resonance. Okay, so the next thing we have to do is the mathematical solution. And since I only have a couple of minutes left, I'm not going to stop. I'm going to do a quick solution of the problem, but we'll analyze it next time. So, and the reason I'm doing this now is I want to make the connection here of the ordinary differential equations. Let's rewrite this equation, dCA dt plus CA over tau is equal to CA in tau. Tau is a constant, CA in is a constant. CA is the variable. What kind of equation is this? This is a first order linear ordinary differential equation. It's linear because I have only CA to the first power or the zero power in every term. It's first order because I have only a first derivative. How do I solve first order linear differential equations? We've all had a course in ODE. How do you solve all linear first order differential equations? There's only one variable that's separated. Integrating factor. What's the integrating factor here? The way the integrating factor is e to the value of t over t times the coefficient of CA. So it's e to the t over tau. Because the coefficient is 1 over tau. So I can rewrite the left-hand side as ddt of e to the t over tau, CA, is equal to e to the t over tau, CA in over tau. How do I know that? Well, if I take ddt of this, I'll get the exponential times dCA dt, the exponential times CA dt, plus CA times the derivative of the exponential, plus CA, derivative of the exponential is a 1 over tau times the exponential. And that's equal to the right side. This is a total derivative, so I can now integrate it. I can integrate from 0 to t. And this is from e to the 0, CA of 0, to e to the t over tau, CA. And what do I get? Here I get CA e to the t over tau minus CA of 0 is equal to CA in over tau times this integral. Well, what's the integral of e to the t over tau dt? Simple now. What about the constant? What's the integral of e to the at? What's the integral of e to the at?
A e to the at.
That's the derivative. What's the integral?
It's e to the at over a.
E to the at over a. So here a is 1 over tau. So it's e to the t over tau divided by 1 over tau. Divided by tau divided by 1 over tau. From 0 to t. At 0, I just, at t, I get e to the t over tau minus 1. And this is counted. Finally, I have CA of t CA of 0 to the minus P over that, plus CA in times 1 minus P to the minus P. And we will analyze this next time. Right, here we have the solution, and it always works this way. And we will start with that next time. Are there any questions? Questions? So what you can see here is we're going to be relying on this basic method of integration from your undergraduate ordinary differential equations class. And we're going to go through this in a bit more generality next time. But I wanted to give you the simple case today. And we'll do the more general case next time. Questions? Okay, please hand in your homeworks to the TA now. If you haven't emailed them to the TA or whatever that's. Why don't you offer the, since I can't hear you through the mouse, et cetera. Okay, are we ready to get the whole thing? Who's in charge of taking pictures of Blackbird? Just send
Email or?
Email.
How big is it?
The blue is apparently the YouTube channel that Etienne is going to create with all of the videos in the classes. So in case you're having trouble falling asleep at night,